Assalamu alaikum. I hope you are all doing great. Okay, so hopefully I'm feeling better today. Wasn't been feeling great these past 2 days, but hopefully we'll be able to do great now. Okay. These days everyone is getting sick, and I was almost sick, but I'm better now. I'm keeping it at bay. Now, so let's start. So earlier what we were doing was we were studying what voltage was, we studied what resistance was, what was the factors of resistance. Okay, and today we're going to have an extremely, extremely important lecture. In fact, it's better that I'm recording this lecture. 1 second. Okay, great. So it's an extremely important lecture, right? In fact, it is the single most important lecture for electricity today. Hopefully, I'll try that we try to cover as much as the chapter as possible. Okay, so we'll be doing lots of questions today. I'll show you how every single one of those questions is done. I would highly recommend that you take notes side by side. Use my video. The video won't be 2 hours long, right? Because it's a recording. Recordings are shorter because I'll be condensing it into the video, and you can watch it over and again and again and again and again. So make sure to watch it. Pause it every few minutes, then try to write it down, then try to solve it by yourself. This is the way you should try to watch this lecture. Try to practice. If you have any questions, you can write it down, and you can either send it to me on text, or we can discuss it in detail in the next class. Okay, so we're going to try to cover the majority of this chapter today, the difficult part of this chapter today. And if you don't get it, watch it again and again and again till you get it. Okay, sounds good. So earlier, what we were doing was we figured out what resistance was, we figured out what voltage is, right? A good analogy to think about voltage, current, and resistance is that if you know that the pipe has a water flow, the water flow can be thought of as the current, right? That's basically the electrons. So that means current is kind of like the flow of electrons or the flow of water. But why is that water flowing? The water is flowing because there must have been a push on that electron, right? And that push is known as the voltage. That's also known as the EMF. It's kind of like the force that is pushing the electrons, right? Then you have in a wire, right? If, for example, if you have a pipe, and next to that pipe you have a push, which is the source of water, then is there anything that's going to be blocking the flow of water? Absolutely. That would probably be the resistance of the pipe, right? So that means if you have a strong push, but the pipe is pretty clogged up, then that means you're going to have a higher resistance, right? It's kind of like the pipe is clogged up. Okay. So, what was the difference between conventional current and electron flow? Electrons actually flow from the negative plate to the positive plate, but conventionally we can think of current as flowing from positive to negative, because all of the textbooks and all of the diagrams have been assumed from positive to negative. We're going to assume that current is from positive to negative, but it's actually the electrons which are flowing from negative to positive. Okay, but from now on we're going to use conventional current. Then, what is potential difference or voltage? That's basically the work done to drive a unit charge across a resistor, right? So if you use up energy to drive a unit charge across the resistor, that's what is basically what voltage is. 5 volts means that 1 coulomb was used up to drive 1 coulomb charge used up 5 joules of energy to get across it, right? Because voltage is basically just work per unit charge, right? So it's basically 5 joules per coulomb was used to drive a 1 coulomb charge across the resistor. EMF is just basically that is that if the EMF is 12 volts, that's also known as the total battery of the volt. That's known as the total voltage of the battery. Then you could say that 12 joules was utilized to drive one charge across the entire circuit, right? So if the battery is 12 volt, that means 1 coulomb will have 12 joules, which will be used up to drive across the entire circuit, right? So the EMF and voltage, they're exactly the same thing, but voltage is the work done to drive a unit charge across a component, whereas EMF is the work done to drive a unit charge across the entire circuit. Okay, so that's the theoretical meaning of EMF and voltage. Now, moving on to the law that connects all of these ideas, the law that connects voltage, current, and resistance. That is known as Ohm's law. Now, how do you define Ohm's law? First of all, I think it's pretty convenient to describe an experiment. For example, what we're going to do is, let's say, this is the exact experiment that this is the guy Ohm, that literally did this experiment. So let me draw 5 batteries. So this is positive, negative. Okay. So I'm going to draw 5 batteries. One, two. In fact, let me draw another one as well. Let's draw another resistor next to it as well. So this is a 1 ohm resistor. Okay. So I'm going to draw multiple resistors and multiple batteries in front of you, and you'll see what I'm going to say in just a minute. Okay. So these are 5 different batteries. The first one is 1 volt battery. The second one is 2 volt battery, 3 volt, 3 volt, 4 volt, and 5 volt. Okay. And oh, I forgot to draw the most important thing. This one, this one, this one, and this one. Okay. Now, what are these red dots? This is the ammeter, 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 and ammeter. These are not the actual symbols, right? This is not the actual symbol of a battery. I'm just showing it to you because it makes more sense to show it like this for now. Okay. So in this experiment, what are you doing? In this experiment, you basically have 5 different batteries, okay? But you have the same resistance that is passing through all of them. Now, what this does is this allows us to explain that what is the relationship between voltage and current while keeping resistance constants, right? So what we noticed was that when we had a battery of 1 volt, we had a current reading of 1 ampere. When I had a battery of 2 volts, I had a current of 2 ampere. When I had a battery of 3, guess what? It's also 3. When I had a voltage of 4, 4, 5, and 5. What do you notice? You notice that as the voltage increases, the current is also increasing, right? But there is a very, very strong assumption over here, assuming R is constant, right? Because notice resistance is the same, assuming R is constant. Now, for example, if you were to try to plot this on a graph, right? If you have like a voltage and current graph, what would you see on that graph? You'd see a straight line passing straight from the origin, right? So this is a straight line. Now, this is one of the most important graphs in electricity. This is a VI graph. Now, this graph says that voltage is directly proportional to the current. And that's absolutely right. Assuming, assuming R constant. And this is what Ohm's law is. This is Ohm's law. Ohm's law, Ohm said that if you keep the resistance constant, then voltage is directly proportional to current. That is the most important law of electricity. In fact, this can also be written in terms of a formula, V is equals to IR, right? Because, for example, if V is directly proportional to I, and you try to open up this proportionality constant, then this is equal to V is equals to Ki, right? Now this K, what is K? What are you keeping constant? The resistance. So this is actually the resistance. So you can make up a new formula which says V is equals to IR. This is the most important formula in electricity. We're going to, in fact, like 99% of circuits are built upon this single formula. V is voltage, I is current, and R is resistance. And now, check this out. If you take the slope of this graph, if you take the slope of a VI graph, what does that give me? Let's check. Slope is known as change in Y over change in X, right? Now, what is the change in Y? Is that change in voltage? And what is the change in X? That's change in I. So it's giving me a value of V over I. Isn't that basically, if you make V over I the subject, doesn't that give you R? So that means if you take the change in voltage over change in I, that's basically the resistance. So that means the slope of a VI graph is actually equal to the resistance. That's actually equal to the resistance, right? That's an extremely important interpretation. That if you take the slope of this, if you take the rise over run of this graph, then the slope is actually going to equal to the resistance. And isn't the straight line gradient mean that it has a constant slope, implying that the resistance is also constant, right? So that means, and we literally saw that the resistance is constant, right? And that's the only way that would form a straight line, right? Oh, by the way, keep in mind, that if you switch the axis, then the slope would actually become 1 over r, right? So make sure you remember that, because then it would not be v over I. It would then be I over v, and I over v would actually be 1 over r. Okay. You can try to, arrange the formula like that yourself as well. If the axis is reversed, then the slope would be 1 over r, right? If voltage is over here and current is over there, opposite. Okay. But if you have a v over I graph, then the slope would be resistance. Okay. Sounds good. Now, question is, why does Ohm's law even make sense? Why does Ohm's law make sense? It says Ohm's law, according to Ohm, it says that V is equal to IR, right? So this tells me two things. First of all, one thing it tells me is voltage is directly proportional to current, assuming R constant. Okay. Now, how does this make sense? Now, think about it. It's kind of like, you remember, current was the flow of water, voltage was the push, it was the source of water. If you increase the voltage, the source of water, right? If you increase the push on water, then isn't the current supposed to go faster? That's absolutely right. It's pretty easy. It's very, you could say, how intuitive, right? That if you can picture it, it makes sense pretty easily. Okay, there's another proportionality over here. Now, that is, if V is constant, R or you could think of it like this, R is inversely proportional to the current. Well, now, why is that, right? But by the way, how do I figure out this proportionality out? V is equals to IR, which means that V over R is equals to I, right? So it's an inverse proportionality assuming V is constant. So that means if R increases, that means current is going to fall, right? So if R increases, I is going to fall. Now, how does that make sense? Again, pretty easy. Think about it. Alhamdulillah. Think about it. If you increase the resistance on something, then it's kind of like this. If you make the traffic flow much, congested, if you increase the traffic, if you increase the crowdedness of the lanes, then wouldn't it be difficult for traffic cars to pass through? That's exactly the same idea over here. If the resistance of the wires increases, then naturally the flow of electrons would be difficult. So that's why current is going to fall. Then what else can you see through the formula? What else? Let's see. R is directly proportional to V. Absolutely. As R increases, voltage increases, assuming I constant. Assuming I constant. Okay. Although this proportionality isn't as significant, right? Because the problem is that if you end, oftentimes, right, this works in only very special cases. Because the problem over here is that if you increase the voltage, then current by default almost always changes as well. So like, you can't keep current constant if voltage is increasing. Okay, so that's the basic idea. So that's kind of like, you could say, a counterintuitive problem. So we can skip this rule. It's not exactly applicable over here, because it can work out theoretically, but practically it's not very possible, because if you change the voltage, then you almost always change the current as well. So then, like, you can't discuss a proportionality. If you want to discuss a proportionality, then that means you have to keep everything else the same. If you want to figure out the effects of voltage and current, then you have to keep R constant. If you want to figure out the relationship between I and R, then you have to keep voltage constant. Okay, so if you want to figure out I and R relationship, then voltage has to be constant. If you want to figure out the relationship between, for example, voltage and resistance, then you have to keep current constant, right? Because you want to study what is the effect of changing one thing, what is the effect of changing one thing on the effect of the other variable. Okay, so these are the most two important proportionality ideas. Okay, now another example. I want you to think of Ohm's law. This is like the Newton's law for electricity. Newton's law for electricity. Think about it. If V is equals to IR, how about, in fact, let me write it down for you. V is equals to R. Let me write down a formula for you, and you will see how it's very similar to that. Check it out. Although they're not, they're not similar in any way. You can't substitute the values in each other. But do you notice that they're very similar? Check out the relationship between voltage and force. Isn't force very similar to the push that you're giving to the electrons, which is voltage? And what is I and A? Current is basically the flow of electrons, right? How quickly they're moving. And is it acceleration kind of like the same thing, right? It's the rate of change of speed, right? So that's very similar as well. That means if you apply a greater push on something, it's going to accelerate. And isn't that very similar to V and I? That if you apply a greater push on the electron, they're going to speed up, right? Very similar. And then mass. If you have a higher mass, that means it becomes very difficult to push that thing. Isn't that very similar to resistance? Right? Because resistance opposes the flow of something. Resistance is opposing the flow of electrons, whereas mass is doing the same thing, right? Mass is resisting the change of state of their motion, right? So resistance is kind of like the inertia to movement of electrons. So these are very similar, explanations. Okay, sounds good. And this is also a great analogy that I've put over here. It's a great piece of text that how you can explain V is equals to IR using, for example, a ball rolling down a slope. Okay, it's just an analogy to better get it around your head. But I think, even this is great so far. But for extra detail and extra visualization, you can read this out. In fact, I've shared a video over here as well. This little video, I've shared it in the group as well. It's an excellent video to visualize what's actually happening in circuits, right? Like, how is it that voltage increasing is increasing the current? And, what is the relationship between current and resistance? You will actually see the visualized flow of electrons and, voltage with an example of a height and a slope. So it's pretty interesting. I recommend that you watch it. Okay. Now, these are the circuit symbols. Hmm. So these are the circuit symbols that I would like you to learn. Now, there are a lot of them, and you don't exactly need to learn all of them right now, but I will tick the ones that are absolutely important. Okay, so but by the way, make sure to practice this yourself and write it down by your hand. It's very easy to mix them up, right? Because a lot of them actually are quite similar. Cell, extremely important. This is a battery. Okay, make sure a battery. Uh, oh. Make sure you remember that a battery actually looks like this. Battery looks like this and a cell looks like this, because a battery is made up of multiple cells. So that means you will have to draw this dotted line in between. Okay. Then this is a power supply, extremely important. This is the power supply. This is a DC power supply, in fact. Okay. We'll see later on what DC and AC is, but I'm sure you probably know. This is a DC power supply, and this is a AC power supply. This is just a junction of conductors, just like connecting wires. This is a lamp. Fixed resistor, great, pretty important. Variable resistor, extremely important. And thermistor, also extremely important. Try not to confuse these two. Make sure to get them, right. Do not mix them up. LDR, light dependent resistor, also extremely important. This is what a heater looks like. This is a potentiometer, also important. We have an entire topic related to this. Diode, extremely important. LED, also very, very important. Make sure to get the arrows right and the shape as well. Okay. Then switch, pretty important. Earth, also important. Bell is not really important. It almost never shows up. Buzzer never shows up. Microphone never shows up. These ones are generally more usable. Let me write it down. So these ones are generally more, you could say, usable in A2 paper 5. Right? That's kind of like the ATP for paper 5. These symbols are very frequently used in A2 paper 5, but in A1, they're not used at all. Like I haven't seen anywhere where they're being used. Okay. So ammeter, extremely important. That's like the single component that you're going to use the most, and voltmeter and galvanometer as well. Okay. So what is a galvanometer, by the way? A galvanometer is a sensitive, zero center ammeter. Right? So although an ammeter and galvanometer are very similar, the ammeter is kind of like that, it starts from just one end and this is the needle, 0 ampere, and then it only increases 1 ampere, 2 ampere, 3 ampere. Whereas a galvanometer is much more sensitive, and it actually has a centered 0 point, and it can give you both positive and negative values. So that means it's going to be centered at 0 volt, and then there's going to be on the right side a plus 1 volt, and then there's going to be a negative 1 volt in the other direction, right? Why is this important? Why do we even care about negative ones? This one is more applicable for AC currents, right? If you have current switching directions constantly, then the galvanometer is more important, because then you can see that how frequently does the current change direction. But whereas the ammeter, that does not tell you how quickly the current changes direction, because it is going to go from 0 back to 1 and 2 and 3, right? So you can see whether the current is changing direction with an ammeter. This is the difference between a galvanometer. Oscilloscope, also extremely important, although we don't really use it much in A1. But I would recommend that you remember this, because they might mix this up with AC current. Because check this out. This is what an AC power source looks like, right? So it might be easy to confuse these two. So I would recommend that you remember this. Capacitor, also A2, entirely A2. You don't need to remember this. Okay. Sounds good. So make sure to write down all of the ones that I've taken. There's like 6 to 7 that you probably don't need to remember, but the rest of them, make sure you've written it down and, learned it. Okay. Now, moving on to probably the single most important, well, not the single most important. I say everything is important, right? But this is one of the key pillars of the circuit theory, right? How do circuits work in series, and how do circuits work in parallel, right? Extremely important. If you get this, then I guarantee that you will be able to solve almost any circuits question for A1, for A2, for O levels, for anything in your university as well related to circuits. Okay, so this one, and we're going to solve pretty tough circuits as well. So, question is, what is the effect? So basically, the idea is, how do circuits work in series, and how do circuits work in parallel? Okay, because oftentimes you don't just have like one of these, you have a combination of these. You have series and parallel together, and you often have to figure out what the current is. You have to figure out what the resistance is. You have to figure out how can you minimize the current, how can you increase the current, how can you reduce the voltage, and so on and so forth, right? So we have to be able to mathematically figure out all of these values, because electricity is all mathematical, right? It's very accurate, in fact. So let's see how resistances work together. In fact, we can use resistances to alter the voltage and current, right? Resistance is our best tool. Resistors are the best tool, right? Like we don't have resistors to like stop current. Resistors are the best tool to control current, right? Because controlling the resistance means controlling the voltage and the current. Okay, and now you'll see mathematically accurately how much that the resistance and the voltage affect current. Best tool to control voltage and current. Okay, so now listen to this picture very carefully. Okay, so I'm talking about series for the moment only. Now, for a series circuit, this means that the resistors are resistors placed consecutively. Consecutively. Okay, now I want you to remember two things for a series circuit. The voltage is divided in all of them, and the current is equal for all resistance. Okay, now if you just remember these two things, then all of the series circuits are built upon this fact. Okay, just remember this. I'll highlight it. Okay, now we'll try to think of an analogy to try to explain how circuits and series work. Okay, now I've got this person over here, and this person has a bag over here. And by the way, this is a battery. These are three resistors. Now, what is current? Okay, current is basically Mr. Charge. Mr. Charge moving. And what is Mr. Charge? This is Mr. Charge. Okay, and that Mr. Charge has a bag. And what is that bag? That bag is basically a bag of energy. This is a bag of energy. Or that bag of energy is basically voltage. Okay, because voltage was just energy. It's just energy for a unit charge. And what is battery? The battery, this is the battery, right? Battery is known as the ATM of energy, right? So think about it. Mr. Charge is the one that's going to travel across this entire circuit. Okay, he's going to travel across this entire circuit and he's going to take his bag of energy with him. Okay, he's going to take his bag of energy with him. Now, where did he get his energy from? From the battery. Now, what he's going to do is Mr. Charge, which is basically, if he moves, then that becomes current. He's going to take his bag of energy, he's going to start running, and so forth. And then he reaches R1. Then at R1, he has a problem. In order to get through R1, he needs to pay an entry ticket, right? And when he pays that entry ticket, there is some energy lost. And what is that energy lost? That is called V1, right? So if you hold a voltmeter at between R1, then if you show, if for example 4 volts was lost over here, that means from his bag of energy 4 volts were lost. So that means now once he has moved forward once he has moved forward from R1, he had to give up a few volts of electricity, a few volts of energy to get to R2. Now, that what happens when R2 is reached? Now, when you have reached R2, that bag of energy, right? R2 has an entry ticket as well. Then R2 is going to have to require some energy for him to pass through. So that means this person moves on from R2, which means that that person had to give up some energy to pass through R2. He gave the entry ticket. Then he is approaching R3, right? And by the way, by this point, his bag is much smaller. His bag is very small now, right? Now, again, R3 has an entry ticket as well, right? So if R3 has an entry ticket, that means he's going to have to pay that cost of energy, and then he will be allowed to pass through. And then finally, he will go without any energy back to the battery. Now, guess what will happen when he reaches the battery? Do you remember what the battery was? The battery was the ATM, right? He's going to take a refill from the battery of energy, right? Once his bag is full, right? Or full of all of the energy that the battery can give, then Mr. Charge is then going to complete the circuit again and again and again and again. And he's going to keep on supplying energy to the resistors, and he's going to keep on supplying energy from the battery. And this is going to keep on happening till what happens? The ATM runs out of energy, right? Or ATM runs out of money. So that is basically how circuits work. V1 is the energy lost to R1. V2 is the energy lost to R2. V3 is the energy lost to R3, right? So these were kind of like the entry tickets for the charge to pass through. If you remember the definition of voltage, that was the energy required to drive a unit charge across the resistor or across the component. Okay. Now, we know that in series circuits, if you want to figure out the total resistance, then the total resistance is basically the sum of all of the resistance. That's it, right? So what that says is that RT is basically just equal to R1 plus R2 plus R3. That makes sense, right? And it seems pretty straightforward. Like, why would we even need to say this? We need to say this because in parallel circuits, this is not the case, right? That's why we need to define this. So they say that prove this equation. This is shown up pretty often in questions as well. Prove that RT is equals to R1 plus R2 plus R3, right? Now, how do we prove this? First of all, you have to know these two facts to derive it. Voltage is divided, right? So by the way, this is the EMF, which is the total voltage provided by the battery. V1 is dropped, V2 is dropped, and V3 is dropped, right? So the most common sense thing that makes sense over here is that E is equals to V1 plus V2 plus V3, right? This is the battery, this is the voltage provided by the battery, and this is the total voltage dropped, right? So you could think of this kind of like this is the energy input, right? Because this is providing energy, and it should equal to the energy output, right? That makes pretty common sense, right? that this is the energy provided by the battery, and this is the energy lost in, providing energy to the resistors, right? So if you remember, V is equals to IR. How about I write this entire equation in terms of V is equals to IR? I absolutely can, right? So IR equal to IR plus IR plus IR. But the problem is they can't all be IR because, right? Because the problem is they're all different resistors. So what about V1? IR is actually the voltage through resistance R1. So you're going to write this is resistance R1. V2 would actually be the voltage drop from R2. So that would also be R2. R3 is going to be this one, right? Because for V3, the resistance was actually R3, right? So, and by the way, for EMF, right? So for EMF, remember this. For EMF, if you're talking about V is equals to IR, because you are talking about the total voltage, okay, then the rest of them would also be total. So if in the formula E is equals to IR, right? If this is total voltage, right? Because E is just another word for saying voltage, then this must also be total, then this must also be total, right? So if you talk about total voltage in the V equals to IR formula, then the current has to be total as well, and the resistance also has to be total. So that means you have to talk about total current over here and total resistance over here. So that means instead of writing E, you could also write IR, but I has to be total and R has to be total. Okay. And by the way, if you remember, I said that current is equal for all the resistance. So that means the same current is flowing through all of the resistors, right? Let's call it IT, which is total current. The same current is passing through all of these resistors. So that means I can say that all of them are basically IT, IT, IT. Okay. So E is equals to V1 plus V2 plus V3. That means, I can replace E with ITRT, V1 with ITR1, V2 with ITR2, and V3 with ITR3. Now, what if I took IT common in all of them? Because it's the same. What does that leave me with? That leaves me with R1 plus R2 plus R3, right? Now, check this out. Do you notice that IT actually cancels out from both sides? And here it is. Proof that RT is literally equal to R1 plus R2 plus R3. All we needed was the fact that energy input equal to energy output. And we just needed the fact that, we just need Ohm's law, right? So we use the law of conservation of energy, and we use the law of conservation of energy, and we use the Ohm's law to figure out that the total resistance equal to R1 plus R2 plus R3, right? So that's how resistances are working in series circuits. Okay. Hopefully you got that. Try to derive this yourself. This is a very known important derivation. If something does not make sense, you can text me and I'll try to clear it out for you as soon as possible. Okay. So this is how circuits work in series, right? We'll definitely do like tons and tons of numerical examples, but I'm just showing you the expressions of how this works. Now, moving on. How do circuits work in parallel? Okay. For parallel, I want you to remember two things. For parallel, it is the current that divides. It is the current that divides, and it is the voltage that remains the same. Voltage is divide, or you could say voltage remains equal. Okay. What does that mean? That means that, oh, by the way, what do we mean by parallel? We mean that different currents in different junctions, right? So what we basically mean is that there are different resistances in different junctions. Okay. In this case, resistances were next to each other. They were placed consecutively like in a train, right? Or kind of like a one-way road. This is kind of like a one-way road. And this is, you could think of this as all of those resistors are placed parallel to each other. They are in a like a three-way road, right? And the three-way road is going forward. There are multiple lanes, okay? Or kind of it's helpful to think of it like as water canals. Think of this as a single very large canal, whereas think of this as the canal being divided into three junctions, right? Those three junctions are called parallel junctions. Okay. Now, so for example, what did we learn for parallel? We learned that current is divided and the voltage remains equal. Now, what does that mean? That means if you have battery EMF E, okay, and the current flows into these three junctions, all three junctions will get the same voltage. Okay, so all three will get the same voltage. But actually, what's going to happen is that in this case, the current is going to divide itself into three junctions. Current is going to divide itself into three junctions, right? So that means it's going to, if the total current is IT, then it's going to divide into I1, I2, and I3. And then once you reach this point, it's going to then converge again and then combine to form IT, right? So what is the total resistance in this case? The total resistance in this case would, you would just say RT is equals to R1 plus R2 plus R3, right? Are these the three resistance? Absolutely not. This is not how resistances are added in parallel. That's exactly why we had to make this obvious. Okay. Now, how do resistances add in this case? In this case, we know that what do we know so far? We know that current divides and voltage remains equal. So how about I say that IT, wouldn't it be fair to say that IT is equals to I1 plus I2 plus I3, right? It's fair to say that. So if that's the case, can I use, that's just saying that, current should equal, that there shouldn't be any current lost. If I say that V is equals to IR, can I rearrange the formula for I? Yes, I can. I is equals to V over R, right? So how about I replace I with V over R? So how about I replace all of these with V over Rs? So let's just write V over R. Hopefully it was recorded. I don't even know if it got recorded. Okay. Hopefully it got, and I will receive the recording later on. Okay. Let me repeat what I was saying. So if I am replacing IT with V over R, then if one of these is total in the formula, then the rest of those values also have to be total. So if I say total voltage is equals to V over R, then that means I have to talk about total voltage and I have to talk about total current, right? And if you remember, wasn't voltage the same in all of the resistors? All of them are getting total voltage, right? So let me replace all of them with VT, VT, VT. And V Why does this keep getting disconnected? Okay, right? So what I was saying was that I2 is basically just equal to E over R2, right? Because I is equals to V over R, and I'm just rewriting it in the same way by just replacing it for their respective values. Okay, so if E over R2 is equals to E R1 plus E over R2 plus E over R3, and if I take E common from, okay, if I take E common, what does that leave me with? That leaves me with 1 over R1 plus 1 over R2 plus 1 over R3, right? And check it out again. E cancels out on both sides. E cancels out, E cancels out. Then what do I get left with? 1 over RT is equals to 1 over R1 plus 1 over R2 plus 1 over R3, and that's it. That's how resistances actually add up in parallel. It's the reciprocals that add up, right? Keep in mind the reciprocals add up and not directly the resistances, right? So this is how you add up total resistance in a parallel combination, right? So for example, if you have a 12-volt battery and these are the parallel resistors, then all three are going to get the same voltage. Okay. And what about the current? So for example, if the total current is 5 amperes, then this 5 ampere current is going to get divided into the resistors depending upon the resistance. Then once their current have divided and then they reconverge, then they become 5 ampere again, right? So this is how current and voltage work in a series and parallel combination. Okay, now what else? All right, so if you were to summarize it, what happens to the voltage, current, and resistor in series? In series, the voltage is going to divide, but in parallel, the voltage is going to be equal in all the resistors. In series, the current is equal, but it is the current that is dividing in parallel. What happens to the resistance? In resistance, RT is basically just equal to R1 plus R2 plus R3, right? But for parallel, it's actually that 1 over RT is equals to 1 over R1 plus 1 over R2 plus 1 over R3. So this is how resistances add up in parallel. Make sure to remember this table. Okay. So hopefully this summarizes the way circuits work. This hopefully summarizes Ohm's law. And this is part one of the lecture. In the next lecture, we're going to discuss how to calculate resistances, how to work with very complicated circuits, how to calculate voltage, ampere readings, how to calculate, series resistance, total voltage, weird combinations of current, weird combinations of, very technical circuit setups. So we'll be spending a lot of time on that. Okay. And that'll be part two of the lecture, which I'll send in just a few hours, hopefully.